Okay, welcome back. We are looking at Unit 2 notes for Math 160 statistics. So let's switch over so you can see what I'm talking about. Here we have exploring data with tables and graphs. Now, because I don't always like to lecture, like I don't always like to be the one talking, a lot of this is typed up so that I don't have to. So can we have a volunteer to start the conversation? We have frequency distribution or frequency table. Who would like to read part A? Just go ahead.
Do you want me to do it?
Sure, thank you.
Reading part A?
Yeah.
Okay. Individual or group shows how data are proportioned among several categories or classes by listing the categories along with the number of data values or frequency in each of them.
That's really important to know. So you can create an individual frequency distribution or a group frequency distribution. So you're looking at how many times something occurs, right? You're looking at what are the observations and then how many times do you see them? That's essentially the idea behind creating a frequency distribution or a frequency table. And Nicola, would you read part B, 1, 2, and 3?
Properties of a group frequency distribution. 1, a table that summarizes data by classes or class intervals. 2, in a typical group frequency distribution, there are usually 5 to 12 classes. And 3, the table may contain columns for class number, class interval, tally, frequency, commutative frequency, relative frequency, cumulative relative frequency, and class mark of class or class midpoint.
I know that number 3 is like ridiculous. Sam, would you continue reading 4, 5, and 6?
You got it. Okay. 4, lower class limits are the smallest numbers that can belong to each other of the different classes. Upper class limits are the largest numbers that can belong to each other of the different classes. And class width, the difference between the 2 consecutive lower class limits or 2 consecutive lower class boundaries in a frequency distribution. Every class interval must have the same class width.
Perfect. Thank you so much. I'm going to make a comment here for class width. At this point, I'd like to kind of sneak in the formula onto your notes, that just so that when you think of class width, you could be like, oh yeah, I wrote down the formula. So when you think of the class width, the easiest way to calculate this is to consider doing the following. You want to take the lower limit of the second class, and then you want to subtract the lower limit of the first class. That is the easiest way to keep that in your minds, the lower limit of the second class minus lower limit of the first class. Keep in mind that it's not limited to just those 2 classes. It's also not limited to just the lower limit. You could, if you wanted to, you could say, take the upper limit of the second class and subtract the upper limit of the first class, right? You could do that as well. So it's not specific to having to be lower or having to be upper. The bottom line is the class width has to be the same across the board. So you can check this from class to class. Does every class have the same class width? Oh, okay. Well, we can check that very easily. Beautiful. We have 7, 8, and 9. Ava, would you finish this off, this page?
Yeah. Class midpoint or class mark, the middle of each class, take the average of the lower and upper limits of a single class to find its midpoint. 8, cumulative relative frequency. The cumulative relative frequency, it is found by adding successive relative frequencies to the previous cumulative relative frequency, and then 9 relative frequency for that class, and some of the frequencies.
Okay, so check out, so there's a couple things here. First, when you see the words class midpoint, which is the same as saying class mark, those are interchangeable. When you think of that, I know I wrote down the idea behind it, the formula behind it in words. And what it is it says, take the average of the lower and upper limits of a single class to find its midpoint. So in a class, you want to take the lower plus the upper, right? So the lower plus upper, and then you divide by 2. That's how you find the average of any two numbers. We know this. So that's how you would find the class midpoint. The lower limit plus the upper limit divided by 2. Now keep in mind that it has to be the same class. You don't want to take data from different classes. That doesn't make sense. So I'm going to make a note here. Lower and upper must come from the same class. Okay, keep that in mind. The lower and the upper must come from the same class if you want to find that class's midpoint. Good. Cumulative relative frequency, just think adding, right? So if you know your relative frequencies, you're just going to add the next one. And I'll show you that. That one's actually pretty easy. Cumulative, accumulate, adding, putting together, that kind of thing. Cumulative, accumulate. And then finally we have, what's that?
It's in the car.
Oh, that's something else. And then we have relative frequency. So there is a formula, I wrote that down on the sheet. So we've got the frequency for that class divided by the sum of all frequencies. This is really important to know. So divided by the sum of all frequencies, that's going to give you the relative frequency. Interestingly enough, that's actually the same as finding probability. Do we remember concepts related to probability? Let's test that idea. So let's just have a conversation for a moment. If I were to pick a card at random from a standard deck of cards, I'm hopeful that by now you've all played cards in some capacity or another. What is the likelihood that I'm going to draw a 10? You know this. How many 10s are there in a deck of cards?
4 out of 54 or 52.
Good. 4 out of 52. That's relative frequency, right? There are 4 10s out of 52. So that's relative frequency, which by the way is probability. What do we know about probability? So for instance, can I say that there is a negative 20% chance that that's going to happen? Is that possible?
No,
Why? Why no?
because
Probability can't be negative.
Okay, because probability can't be negative. I love this. Thank you. So what if I said, I know for 120% fact that that's definitely going to happen. Like I'm telling you 120%, it'll definitely happen. Can I make that statement as well?
no, because you really can't have a probability over 100%.
Perfect. So we're honing in on the fact that realistically, mathematically, probability sits between 0% and 100%. In terms of fractions or decimal values, that means probability sits between 0 and 1. That's something that I want you to consider. You can't have probability that's greater than 1 in value, right? And you can't have probability that's smaller than 0 in value. When we refer to percentages, that's 0 to 100, but we can turn every fraction into a percentage. We know how to do this. Okay, just wanted to throw that out there so that you're not thinking that this is something that you've never seen before. You've seen probability all the time. We just don't always call it relative frequency. Cool. Let us turn the page. Practice problem number 1. The following data shows heights of trees found at Highland Park measured in feet. Let's complete the following items. So for part A, we're going to start by constructing a frequency distribution with a first class of 18 is less than or equal to X, which is less than 24. Check it out. I've written out the first class here. I do want to point out that there are some practice problems you'll have to do where I give you the first and I don't give you the rest, but you'll have to follow the pattern. And we'll talk about what that pattern is. Notice where one class interval ends, the next one starts. Include columns for frequency, cumulative relative frequency. Wow, that's a mouthful. And then of course, class midpoint. And then for part B, we want to identify the class width. So here are all the trees at Highland Park measured in feet. Okay, and obviously it's just a sample of the trees because that park is huge. So I want you to first be critical about what you're seeing in terms of tree heights. Notice the inclusion, exclusion. So 18 is less than or equal to X, which is less than 24. What this implies is that the values that will fall in this class will be anywhere from 18 all the way up to, but not including 24. Does that make sense? So it would be all the values, including 18 up to, but not including 24. So 23. If we had decimals, it could be 23.6, 23.9, but it can't be 24. Okay, that is the reason we use these inequality symbols like so. Notice that this first class looks like it ends at 24, but we know that it doesn't include 24. So the next class begins at 24 inclusive. So in our second class, we have all of our tree heights from 24 up to, but not including 30. Does that make sense? Score. Okay, so what I like to do personally is I like to write tally marks as I do this, especially when you have data that's all over the place like this. I do not like to look for them and then mark them down. I simply say, okay, we have 27. That means we are in the second class. I'm going to put a little tally mark. We have the next height, which is 23 feet. So that's going to be in our first class. And I'm put a little tally mark. So I want us to continue in this fashion. You can watch as I move through this, or you can do this at the same time, and then we can reconvene. So go ahead and throw your tally marks in to account for the heights of all of your trees. And I'm going to move this up just a touch so that you can see everything that I'm doing. If you have any questions while I'm moving through this, please tell me. Be very careful as you assign each value. When you're all done, verify with my chart that you have counted the same values for each of your classes. I do want to represent your class intervals in interval notation, just in case you see this in Lumen as well. This interval 18 is less than or equal to X is less than 24. You can actually write it in interval notation using brackets, comma, and then parentheses. So bracket 18, comma 24 is another great way of saying it has to fall in this interval. It's inclusive of 18, but it doesn't include 24. Same thing with the second one. You'd use bracket 24 because remember it's closed on 24, but it's open on 30, meaning it doesn't include the value 30. So that's just another way of representing your interval. That is interval notation. Hopefully you've seen this in either 098 or 096. Next, we want to write out our relative frequency. When you think relative frequency, I want you to think probability. What is the likelihood that you will pick a tree that falls in our first interval? Well, in order to do relative frequency, we have to know how many values we have in total. How many trees did we measure? The easiest way to do that is to check your frequency. How
25.
Perfect. So there's a total of 25. What we may want to note here at the bottom is we can say that the total is 25. That's going to be really helpful to us just to have that little note there. We verify here and then we add our frequencies because we want to make sure that our data values and the frequencies match. I've seen students accidentally leave a frequency off. So if they added this, they would say 24 and they'd be like, oh shoot, I missed one. So let's make sure that those two definitely line up. So for relative frequency, we're taking the probability that we pick a tree that is anywhere from 18 feet up to, but not including 24 feet. And that's simply an 8 out of 25 chance. Right? That's the probability. So punch that into your calculator, 8 divided by 25, because I'd actually like a decimal. Anyone who's taken my classes before will be like, now she wants decimals. Okay, because pretty typically I always work with fractions.
0.32.
Thank you. 0.32. We're going to continue through this same fashion for each class. The second class, the likelihood is 7 out of 25. For the third, it's 2 out of 25. For the fourth, it's 6 out of 25. And then we have 1 out of 25 and then 1 out of 25. I would like those respective decimals. Would somebody shout out 7 over 25 is?
0.28.
Beautiful.
0.
Someone else. 2 out of 25. Thank you, Chingy.
0.08.
108.
Yeah, 0.08. Give me the next one. Someone else.
0.24.
Beautiful. And then, of course, 1 out of 25 is?
0.04.
Beautiful. And that's the same for the last one. Excellent. That's relative frequency. Think probability. What are the chances, right? What's the likelihood? Cumulative relative frequency, no big deal. I'll write out exactly how you do this. So first off, for your first class, there's no accumulation. It's literally just what we have for relative frequency. So it's 0.32. But when we move to the second class, what we're saying is, what are the chances now that your tree height will fall from anywhere from 18 feet all the way up to, but not including 30? Accumulate, right? You're now looking at two classes and you're combining these probabilities to get cumulative relative frequency. So for this one, you're just going to take the 0.32 and you're going to add the 0.28. When you combine those, you should get 0.60. For the third class, we want to know what are the chances that you will find a tree whose height is from 18 feet all the way up to, but not including 36 feet. So you want all of these relative frequencies combined. So we want 0.32 plus 0.28 plus 0.08. And when you add those three, you get 0.68. Now, we could continue to write out each of these, but you're obviously seeing here, you start with the first one. To get the second, you add these two relative frequencies. To get the third, you add the 3. To get the 4, you add the 4. You see, you get the gist here. So let's actually add these up. What's 0.68 plus 0.24?
0.92.
Beautiful. Take the 0.92, add 0.04. That's going to give you 0.96. Take the 0.96, add the last little bit here, 0.04, and guess what? It gives you 1, which should be no surprise to you because total probability is 1. That takes into account all of the trees that we measured. Perfect. Not bad, right? I love it. Last but not least, we must find the class midpoint. Now, this may make you a little bit worried because of the fact that we're going to take the lower limit and the upper limit, add them, then divide by 2. And you might say, well, the upper limit's not actually 24. Yes, but we're not going to get that technical, okay? So because we've used these bounds, 18 and 24, to define this class, we will use those values for our formula, okay? I don't want you to overthink it. So you're going to take 18, you're going to add the 24, the lower limit and the upper limit, and you're going to divide by 2. So we have 18 plus 24, punch that in, it gives you 42, divide by 2, and we find that the class midpoint, the middle value, is 21. And that's a process you're going to take for each of these. So we have 24 plus 30, and then you divide by 2. So you're looking for the exact middle.
27.
Yeah, thank you so much, 27. What's the next midpoint?
33.
Beautiful. The one after that?
39.
Excellent. Keep going.
45
45.
and 51.
45 and 51. Perfect. And there you have it. Those are your class midpoints. Perfect. So for part A, we did exactly what we were expected to do. We had frequency, relative frequency, cumulative relative frequency, and then finally class midpoint. For part B, we want to identify the class width. So I'm going to write B down here, and I'm going to write class width is equal to, recall our formula. What I mentioned to you was taking the lower limit of the second class and subtracting the lower limit of the first class. In each class, you see a lower limit and an upper, lower limit and an upper. So we are going to take the lower limit of the second class, which is 24, and I'm going to write lower limit of second class. I'm just making a note here so that when you go back, you're like, oh, that's how she did it. And then you're going to subtract the lower limit of the first class, which is 18. So lower limit of first class. 24 take away 18, that's 6. So that's a class width. So essentially that's a width between classes, right? So if you took 30 minus 24, you'd get 6. You take 36 minus 30, you get 6. 42 minus 36, you get 6. So anywhere you move in this particular frequency table, your class width will always be the same. And that's the point. Okay, when we think of class range, range is a little bit different. Range is just high minus low. So that's always going to be 1 less. Okay, typically. Okay, very cool. Let's go ahead and turn the page. Your turn. I want you all to try this practice problem number 2. Just so that we're reading this correctly, there are 64 families, and what I've done for you is I've recorded the number of children that they have, and I've put it in order so that you don't have to like sift through all the data. So you can literally say, well, the number of families that have 0 kids are 1, 2, 3, 4, 5, 6, 7, 8, right? So let me start this off. So the number of children, if the number of families that have 0 kids, we said there are 8, right? Let's do one more. The number of children, there are several families that only have 1 kid. How many exactly?
11.
11.
11, perfect. Okay, you're off to the races. Go ahead and finish this chart. I'm gonna pause the video. Let's reveal our frequencies. So for the number of children, you had anywhere from 0 to 9 kids. Wow, that's a big one. Abby, no worries. Thank you for letting me know. Yes, Marlon, which one? Could you give your full name? So we have frequencies for each of these families. Relative frequencies, we know that there are 64 families, so it's a likelihood that they have 0 kids is 8 out of 64, 11 kids is 11 out of 64, that kind of thing. And those are your frequencies. Thank you so much, Marlon. So we have our relative frequencies. Next, you have your cumulative relative frequency, and all we had to do was simply add the relative frequencies together as we move from one to the next, okay? So go ahead and make sure that your values match mine. I do want to point out that you're probably looking at this and being like, but we said probability cannot be bigger than 1. While I agree, we're also rounding, so there's definitely going to be some rounding error. Ava, what's going on?
Can you do like an example about how you got the cumulative relative frequency?
Yes, absolutely.
Just like, yeah.
So for instance, with this first one, we have just our relative frequency of the first class, which is our observation, 0 kids. If we want the cumulative relative frequency for the next one, we would take our relative frequency from the first class and add the second. So that's how we'd get the 0.297. So think about, I wish I had like an interactive kind of way of showing this to you. So my best advice is if you want to find the cumulative relative frequency of a specific class, you're going to add the relative frequency of the class and everything before. So for instance, if I want the cumulative relative frequency of the third class, we will take this relative frequency and add everything before it. So 0.125 plus 0.172 plus 0.281, that's going to give you 0.578. Does that make sense? If we want the next one, it's the same idea. To get this cumulative relative frequency, you add these 4.
Got it. Thank you.
You're very, very welcome. Awesome. Perfect. Any other questions for me? Cool. All right, let's turn the page. Hopefully I'm not moving too fast. Let's take a look at histograms. Surujni, would you start us off by talking about histograms? And you can read that whole section for part A.
Okay. Histogram A bar graph representing a frequency distributions of a quantitative variable. A histogram is made up of the following components. 1, a title which identifies the population of interest. 2, bars of equal width drawn adjacent to each other unless there are gaps in the data. 3, a vertical scale which identifies the frequencies in the various classes. And 4, a horizontal scale which identifies the variable x.
Thank you so much. That was perfect. With histograms, you'll notice that while the bars are of equal width and they are adjacent to each other, What I mean by adjacent is that there are no gaps in the bar graph. So here's your standard bar graph. I'm just going to draw a little image here. Oh my gosh, this is smearing. So here's a little image of a bar graph. Right? That's not a histogram. That is not a histogram. When you think of histograms, they're a special type of bar graph where the bars are actually adjacent to each other. So they touch each other. So it's kind of like that. Okay, that's a histogram. There are no gaps between the bars unless there's a gap in the data. So for instance, something like that. Man, isn't my drawing so beautiful? My gosh, such an artist. Can't even stand it. Oh, God. I can imagine yours are much better than mine. I would bet anything that they are. Okay. Anthony Fortunato, would you please read B for all of us?
Important uses of a histogram. 1, visually displays the shape of the distribution of the data. 2, shows the location of the center of the data. 3, shows the spread of the data. And 4, identifies outliers.
Very cool. Excellent. When you think of the word outliers, I just want you to think extreme values, like really extreme, not just like a couple points away, right? We want to think like extreme. Let's go ahead and turn the page and play around with a histogram and answer a bunch of questions. The nice thing about histograms is that we've seen these before. We just haven't really tackled them in the way that we are right now in this stats class. So let's take a look. We have theme park admission, and we have the costs. $7 to $14, $15 to $22, $23 to $30, $31 to $38, and then $39 to $46. And then the frequency here is the number of parks. So you have the cost to enter the park, and then the number of parks that charge you within that range. So we're going to use this data to answer the following questions. And what I'd like to do is prove to you all that this is essentially just taking the opportunity to read a graph and dissect it very carefully. And I would love to see you do this together in your groups. So I'm going to assign you into groups automatically. We're going to do, let's do 10 groups. So there will be only 3 participants per group. And I'm not going to set a time limit, but I will come and check on you to make sure everyone's okay. And then it'll close after 10 seconds of me actually closing it. All right, go ahead and join and I'll come check in. Very nice. Let us look at practice problem number 3. What do we have? So for number 1, what is the class width? What did you say?
8.
Yes, 8 is correct. And how did you find that?
I did the lower limit of the second class minus the lower limit of the first class, so 15 minus 7.
Beautiful. Number 2, approximately how many admissions tickets have it cost less than $39? And your answer was?
19.
19. And how'd you get 19?
I added up all the bars.
Good. So you're saying the first one had a frequency of 5, right? The second one had a frequency of 7. The third had a frequency of 4. Then we have 1, and then we have 2, just so that we have all of the bars actually labeled. And so less than 39, you want to add the first 4 bars. Very cool. And is that 19?
The first 4 bars, so you're not adding the last one?
Ah, yes, we are not adding the last one.
15.
15? So
I got
17.
17.
17. Cool. This is why we do this together. I love this. I love this because we check it out, we come up, we kind of dialogue, and then we settle on something that we're happy with. 17 parks is correct. Approximately what percentage of admissions tickets are at least $23? How do we do this?
Maybe 12.
So 12%, tell me more.
It would be 63% because 12 divided by 19 is 63%.
12 divided by 19. Okay, so the first thing you considered is that with percentage, you need part over total, right? And then we multiply that by 100. So I'm going to write times 100. Well, the total is 19. Out of all the bars, there are 19 parts. At least 23 means what? What does that mean, at least $23?
23 or more.
Yeah, 23 or more. So 23 or more consists of these 3 bars, which is 7. So then we have 7 out of 19. We punch that in. Notice that when we take 7 over 19, that gives us this decimal, 0.3684, etc. I'm going to write 0.368. I'm going to round to 3 places. I've been feeling 3 decimals today. That's just like the energy of the day. So hopefully you can agree with that. And then multiply it by 100 for a percentage of 36.8. That at least piece is going to be a little tricky, so just be super careful. Like I was talking to another group, I was like, if I said to you, I need at least $50 to get into this club, how much money do I need? Then it's 50 or more, right? And clubbing, I mean, who goes clubbing? Not me. So at least 50 is 50 or more dollars. Otherwise, you're not going to be able to do anything. So I want you to kind of keep that in mind and think of something fun that's relatable. They could be like, oh yeah, of course, I know what at least means. 4 was tricky. I was able to talk to several groups about number 4, approximately how many admissions tickets are between 17 and 32. We could get creative with it and try to say, like, what if we take averages of these bars, right? Or averages of like the first and the last and then add the middle. I'm going to tell you that you shouldn't do that and you can't do that because we actually don't have enough information. So in one of the groups, I was talking to Kelly about the fact that, for instance, with this second bar, 15 to 22, there's no reason to say that it could be or it should be any other value than, for instance, 15, right? What if all 7 recorded values were $15? Even though the range is from 15 to 22, it doesn't mean it has to span that entire range. The actual data could all be 15, right? So we have to be really careful with that. There's no way of knowing. So we don't have sufficient data. To answer. We just don't, there's not enough information. We don't have it. Beautiful. Next, we have approximately how many admission tickets are more than 14, but less than 39. And your answer?
I got 12 tickets.
I have
12
12.
tickets.
Wow, beautiful. Very, very nice. And really, it should say how many parks, but it's okay to say how many admissions tickets. It's like we're counting the ballots. That's totally fine. There are 12. Number 6. For number 5, because we want more than 14 but less than 39, that means we want anywhere from $15 all the way to $38, right? So like that's the range of values. So then we say 15 all the way to 38 is just these 3 bars. And that's
So you just add them?
Yeah, exactly. 7 plus 4 plus 1. Beautiful. Approximately how many admissions tickets are at most, notice the difference between at least at most 22. Your answer?
12.
12 again.
Correct, exactly. When you think of at most, think 22 or less, right? So at most 22, that means we're looking at these first 2 bars. 5 and another 7 make 12. And lastly, approximately what percentage of admissions tickets are between 31 to $46. What's the fraction that I begin with?
3 divided by 19.
Score, part over total. 3
I got 15.8%.
Me too,
15.
15.8%.
Did we all get 15.8?
Yeah.
Beautiful. And you're done. Nice job. Very, very nice. I love the dialogue. I loved coming into a lot of the rooms and seeing that we might have started quiet, but then we were willing to have those conversations. So when you're in breakout rooms, just take yourselves off of mute and work together, okay? That way you save time as well. Any other questions on page 6? Cool. Hearing none, let's go through the rest of this. I actually think I'm going to be able to finish this in our last 7 minutes, believe it or not. Okay, common distribution types. Here we're just looking at what they look like, right? We just want to know visually what they look like. So we have something called a bell-shaped curve. And a bell-shaped curve, what's really cool is the fact that your mean, your median, and mode are all actually the same value. So that's going to be here. That's going to be your mean, which is the same as your median, which is the same as your mode. Notice that if we were to cut this curve in half, it would be identical on either sides. It's the same percentage of values on either side of that bell-shaped curve. So that's normal. Next, we have a uniform distribution. Notice that your probabilities are exactly identical for each of your values. That's rectangular or uniform distribution. You have something called J-shaped. There is no tail on the side of the class with the highest frequency. So I'm going to draw over this, and hopefully this isn't like, distracting to you, but think of this as like J, okay? Where the highest value here, the highest frequency, there are no values to the right of it. So you have this perfect J distribution here, that J-shaped. Next, we have skewed distributions, which are actually pretty common. The ones you'll see in this class are either normal or skewed distributions. So we have something called skewed to the left. Notice that the tail goes towards the left-hand side, so it's skewed to the left. Okay, that's actually really important to kind of note here. One of the ways that might help you to remember this is think of like, taking a person, putting them on top of the highest peak and then say, go ski. Well, they're probably not going to ski this way. That's really treacherous. So they're probably going to ski this direction to the left. So we have a skewed left distribution. And then for the second one, we have skewed to the right. And you can kind of see that visual here. Again, if you threw a person at the top of this mountain, they're probably not going to skew in this direction because it's so steep. They're probably going to skew to the right or ski to the right so that they're safer. Okay, so you can kind of get a sense of, skewed to the left or skewed to the right, just visually what how this looks based on how it looks. Cool. Next, we have a bimodal distribution. So for instance, notice that there are two bars with the greatest frequency that are pretty similar, but they happen in separate intervals. So for instance, with this particular example, I thought this was kind of a clever way of describing the length of time dentists spent with their patients. So you have like this typical area here, and then you have this group above. What do you think is the difference between the patients who fall in this region and the patients who fall in this one? What's the difference between these patients at the dentist?
Might need more work done.
Yeah, absolutely. Exactly. Starin's like, well, no, duh. They probably need a lot more work, right? And there's a group of people who need a lot more work. And then there's a group of people who are just doing routine checkups. So those checkups are going to be pretty quick. right? Which makes sense. We would have a bimodal distribution here. Bimodal by 2. Good. Okay. Let's label these. Take a look at that first visual. What kind of distribution do we have here? Shout it out.
What's your vote? A normal distribution?
Normal
Bell. Oh,
distribution.
sorry.
Yeah, normal distribution. This second one, hours spent playing video games on weekends.
J-shaped.
Yes, J-shaped.
Screw to the left.
This one?
This one screw to the right.
Yes, skewed to the right. Good. Oops, I can't write. Skewed to the right. Yeah, you definitely want to go towards the right side of this. Awesome. Didn't study, did study.
Bimodal.
Bimodal.
Bimodal distribution, that happens a lot. You can collect this data very easily. And then our last one. Yeah. Skewed.
Oh,
Very nice. And just like that, like I promised you, we are officially done with Unit 2. Awesome, everyone. So I will see you on Wednesday and we'll talk about more assignments that are due, but I don't want to talk about that other than what you have to do already, and that's Unit 1. Focus your energies on your Unit 1 homework, and I will see you all on Wednesday.
oh.
Adios.
Thank you.
Are you okay?
Professor?
Yes.